Welcome, this is the third video of a playlist about the preparation of piperidines. This is a PDF version of the slides under the Community tab of my channel. In this video I'll show you some convenient strategies for preparing piperidines with substituents at position 4. I could not find any natural piperidines with only alkyl or aryl groups at position 4, but there are many synthetic drugs with this substructure. Piperidines with one or two substituents at position 4 have a plane of symmetry and are therefore not chiral, what is a huge advantage in drug discovery and manufacture. First, some general strategies for preparing these compounds. Polar organometallics sometimes add with high selectivity to position 4 of pyridines or pyridinium salts. Addition at position 2 can, however, also occur, and in part 1 of this playlist there are some examples. 2-pyridone is a useful starting material for piperidines. The main tautomer in most solvents is the lactam. Nucleophiles add to positions 2, 4 and 6, while electrophiles tend to attack the heteroatoms and positions 3 and 5. 2-pyridone can be prepared from pyridine. Oxidative amination, the so-called Chichibabin reaction, and oxidative chlorination of pyridine occur at position 2. The direct oxidative hydroxylation of pyridine with hydroxide does not work well, however. But pyridinium salts can be oxidized to pyridones, and there's an example in the first video of this playlist. Unsubstituted 2-pyridone can be obtained either from 2-chloro or 2-aminopyridine, and can be partially reduced with a selectride. Alternatively, 2-aminopyridine can be reduced with lithium to an imine. Both these products are good Michael acceptors and will react with soft carbon nucleophiles at position 4. Another convenient way to prepare 4-substituted piperidines is by olefination, acylation or alkylation of the methyl group of 4-methylpyridine, followed by catalytic hydrogenation or chemical reduction. Quaternized picoline will react in a similar way. 4-piperidinones are another valuable starting material for substituted piperidines. 4-piperidinones can be obtained from 4-hydroxypyridines or by twofold alkylation of primary amines with acrylates followed by Claisen condensation and decarboxylation. Treatment of 2-propenylarenes with formaldehyde and amines under acidic conditions yields aryl pyridines, aryl tetrahydropyridines, or hydroxymethylated pyridines or tetrahydropyridines. Thus, careful optimization will be required to achieve acceptable yields of one given product. A number of optimized procedures have been described in patents. I'll show you now some specific examples of piperidine preparations. This is a typical example of the 1,4 addition of a polar organometallic to activated pyridine. Activation was achieved by acetylation with acetyl chloride. With a small amount of copper iodide, the addition of an aryl magnesium bromide occurred mostly at position 4, and only 2% of the 2-arylated dihydropyridine was formed. Catalytic hydrogenation then yielded the final piperidine. Usually, these 1,4 additions work best with acceptor-substituted electron-deficient pyridines and with soft carbon nucleophiles. In this beautiful example, a substituted 1,4 dihydropyridine was prepared in high yield from inexpensive starting materials. Tosyl chloride activated pyridine, dehydrated acetoacetamide to a nitrile, and converted a ketone into a vinyl sulfonate. The product offers many possibilities for further synthetic transformations. Here, isopropyl magnesium chloride added cleanly to the 4 position of 3-chloropyridine. The resulting bis-enamine then reacted as electrophile twice and with high diastereoselectivity with 1-methyl-indole. In this example, a 4-ethylpicoline-derived enamine was added to the 4 position of pyridine hydrochloride. Hydrogenation led to the selective reduction of the dihydropyridine. Also, silyl enol ethers can be suitable nucleophiles. Here, acylated ester enolate added to 3-cyanopyridine, and after benzylation, the target dihydropyridine was obtained in excellent yield. 3-cyanopyridine can be activated further by quaternization. In this example, with the aid of 10% of a chiral diaminocarbene, butanal added cleanly and enantioselectively to position 4 of the pyridinium salt. Careful hydrogenation reduced the more reactive of the two CC double bonds, while the push-pull olefin remained intact. Diaminocarbenes, like cyanide, can reverse the electrophilicity of aldehydes and convert them into nucleophilic acylating reagents. One problem is that these catalysts will also dimerize aldehydes to benzoenes, and an excess of aldehyde will usually be required for the coupling to other electrophiles. As said, 4-methylpyridine is acidic and can be condensed with aldehydes or ketones. It can also be oxidized to an aldehyde and then condensed with ketones, as shown here. Strong acids can convert tetrahydropyridines into highly reactive dications, and these can alkylate arenes. In this example, 4-phenylpiperidine was prepared this way. Usually both cations will tend to be as far away from each other as possible, but with some starting materials, unexpected products may result. Instead of olefins, also alcohols can be used for Friedel-Crafts alkylations with the dicationic piperidines. One equivalent of water will be released, however, and will deactivate the acid. Here, an excess of aluminum chloride was used to bring about the alkylation. Mannich products aren't very stable and readily decompose upon heating. Here, the Mannich product of acetophenone, formaldehyde and dimethylamine was heated with phenethylamine, and a low yield of a substituted hydroxypiperidine resulted. Heating with an excess of aluminum chloride and benzene gave a high yield of a 4,4-diphenylpiperidine. The debenzylation probably proceeded by intermediate formation of a benzoyl cation, which either decarbonylated or reacted with benzene. Dihydropyridones, like the starting material in this example, are good Michael acceptors and react with soft carbon nucleophiles at position 4. Here a huge excess of a phenyl cuprate was used, and the intermediate piperidinone was reduced to the piperidine with borane. Such Michael additions can even be run enantioselectively. Here, with the aid of a rhodium binap-type catalyst, a boronic acid added with high enantioselectivity to a dihydropyridone. Sometimes even Grignard reagents add preferentially to an activated alkene and not to an ester. Here, arecoline reacted with a slight excess of an aryl magnesium bromide with high selectivity at the olefin. The stereoselectivity was poor though. The Heck reaction is another strategy to introduce aryl groups at position 4 of partially reduced pyridines. Here an intermediate aryl palladium complex was generated from a diazonium tetrafluoroborate, and the Heck product was obtained in excellent yield. Protected piperidines with an activating group at position 4 can be lithiated and arylated or alkylated at this position. Piperidine carboxylic acids are usually prepared by hydrogenation of pyridine carboxylic acids, which in turn can be obtained by oxidation of methylpyridines. Here a methyl ester enolate was arylated with a pyridyl palladium intermediate. This here is a typical synthesis of a 4-benzoyl 4-hydroxypiperidine, just to show some synthetic possibilities. The intermediate bromoketones can also undergo Favorsky rearrangement to 4-aryl 4-carboxypiperidines. Thus, protected piperidines are stable and remain unchanged under a broad variety of conditions. Only strong oxidants, in particular hydride abstracting reagents, may attack the nitrogen-bound methylene groups. The interesting step here is the last one, the alylation of a lithiated tetrahydropyridine. The required starting material was prepared by Suzuki arylation of a vinyl triflate. Treatment of the resulting allylamine with zec-butylithium gave a delocalized carbanion which reacted with allyl bromide with high selectivity at position 4 to an enamine. These can usually be reduced to piperidines with borohydride under slightly acidic conditions. The same strategy can be used to prepare 4-methylated tetrahydropyridines. These enamines are nucleophilic at position 3 and can be alkylated, for instance with iminium salts, as in this example. The resulting product was similarly unstable as a Mannich product, and upon catalytic hydrogenation the dimethylamino group was lost. Protected 4-piperidinones react like most other ketones and can, for instance, be olefinated with phosphonates and strong bases. One potential side reaction is fragmentation of the starting piperidinone by beta elimination, but this did not occur here. With strongly electron-withdrawing protecting groups, however, such as sulfonyl or benzoyl groups, such a fragmentation can occur. Here, mostly the expected alkene resulted, together with a small amount of an isomer. This here is an example of the addition of phenylmagnesium bromide to a 4-piperidinone. An excess of magnesium chloride had to be added, because otherwise the Grignard reagent only acted as a base. With only one equivalent of phenylmagnesium bromide and no magnesium chloride, only the aldol dimerization product was obtained. Nucleophilic substitutions at cyclohexyl or piperidinyl halides are difficult and tend to yield mainly elimination products. More convenient is their conversion into organometallics, which can then be alkylated or arylated by carbon electrophiles. Here, protected 4-piperidinol was transformed into an iodide and then an organozinc intermediate. Coupling with an aryl palladium complex gave a high yield of a 4-aryl piperidine. With the aid of a cobalt diamine complex, the same piperidinyl iodide could also be coupled directly with an aryl magnesium bromide. In this example, an epoxide reacted with copper iodide and an excess of Grignard reagent, first to an iodide and then to a 4-aryl piperidinone. In principle, only catalytic iodide was required, and displacement of iodide by iodide in the intermediate could have led to a mixture of diastereomers. Nevertheless, despite the large excess of copper iodide, mainly one diastereomer was formed. Let's check some examples of cyclization reactions. 4-piperidinone, a valuable intermediate for the preparation of 4-substituted piperidines, can be prepared from primary amines and acrylates by intramolecular Claisen condensation and decarboxylation, as shown here. This strategy even works for acylated piperidinones. The strongly alkaline conditions of the Claisen condensation can cause beta elimination of an amide, but this did not happen under the conditions shown here. Also, simple aldol condensations can give access to 4-substituted piperidines or piperidinones. Here a malone amide was condensed with a ketone, and the product could be hydrogenated with a soluble rhodium complex with high enantioselectivity. Protected beta-amino esters may also serve as starting materials for piperidines. After conversion into a phosphonate, Wittig reaction with aldehydes yielded unsaturated ketones, which were cyclized by stirring with an excess of trimethyl orthoformate and catalytic acid. Piperidines can also be prepared from diethanolamine-derived dielectrophiles. These reagents are often cytotoxic and should be handled with care. Here a non-symmetric diethanolamine was prepared from propylene oxide and a huge excess of ethanolamine to prevent reaction of the product with the epoxide. This large excess of ethanolamine might not have been required because diethanolamines are poor nucleophiles and are difficult to alkylate or acylate. Anyway, reaction of the ditosylate with deprotonated phenylacetonitrile gave the target piperidine as a mixture of two diastereomers. Again, an excess of reagent was used, what was a bad idea in this case because it increased the amount of non-cyclic alkylation products. A similar product as the one of the previous slide can also be prepared from a 1,5-diol. These are accessible by reaction of a given carbon nucleophile with two equivalents of oxirane. Here the diol was converted into a bis triflate and then cyclized with benzylamine. Another elegant way to prepare 4-substituted piperidinones is by hydrogenation of 4-cyanobutyrates. These can be prepared in high yield by Michael addition of cyanoacetates to cinnamates, as shown here. In this instance the diester was hydrogenated, but it may also have been saponified and decarboxylated prior to the hydrogenation to obtain a non-carboxylated 4-aryl piperidinone. Here, a cinnamic acid amide underwent an enantioselective Michael addition with propanal and 20% of a proline-derived catalyst. Reduction of the product with triethylsilane gave the target piperidinone with excellent enantioselectivity and yield. With the same catalyst, a nitropyrrosole was added with high enantioselectivity to an unsaturated aldehyde. Reductive amination then yielded the expected piperidinone. Here the polarity of cinnamic aldehyde was reversed with a chiral heterocyclic carbene, just like I showed you on an earlier slide. Conjugate addition to a nitroethylene yielded an intermediate 5-nitropentanoic ethyl ester, which was reduced to the piperidinone with zinc in acetic acid. Another intriguing way to prepare piperidines is the cyclization of protected diallylamines. With 10% of a chiral nickel complex, such a cyclization proceeded under mild conditions and with high enantioselectivity. Also, boranes can bring about the cyclization of diallylamines, as in this example. The products could be oxidized to alcohols or amines or coupled with carbon nucleophiles. Homoallylamines can be cyclized to piperidines with a Prince reaction. Here an enantiomerically pure homoallylamine reacted cleanly and with high diastereoselectivity with butanal to a 4-hydroxypiperidine. Heating DMSO with hydrochloric acid can yield chloromethyl thioethers, which are synthetic equivalents of formaldehyde. In this example, a homoallylanilene underwent a Prince-type cyclization when heated with DMSO and HCl, and a 4-chloropyperidine resulted in high yield. This is an example of tetrahydropyridine preparation by hetero-Diels-Alder reaction. A rhodium complex catalyzed the cycloaddition of an aza-1,3-diene to a silylated alkyne. Protonolysis then yielded the desilylated product. I mentioned already that 4-piperidinones can fragment by beta elimination. This will occur particularly easily if the amine is acylated or sulfonylated with a powerful electron-withdrawing group. However, even aliphatic amines can be eliminated under suitable conditions. Here, heating a 4-piperidinone with ammonia in ethanol caused complete elimination of a propagylamine. Nevertheless, under aprotic conditions and in the absence of nucleophiles, 4-piperidinones can be sufficiently stable, even in the presence of strong bases. I've shown you several examples earlier. Here's a selection of some more, mostly newer references, which you can also find in the description of this video. Under the Community tab of my channel, there's a PDF version of the slides. This was the last video of this playlist. I hope you got some new ideas out of it, and stay tuned for more videos on synthetic organic chemistry.